So Ruben talked a little bit about history, and I don't really have a history slide, but the School of Mines has been involved in membranes ion conduction for probably 20 or 30 years. And we have this Colorado Fuel Cell Center, which has been up and running for about 4 or 5 years now, which also plays a large part in this. We have very much an expertise from molecules to systems in both PEM systems and in SOFC. So why are membranes important? Well, if you want renewable energy and you want to store it and then convert it and do something useful with it, you're going to need a membrane. We have PEM fuel cells. I mean, PEM fuel cell cars are real. They just cost too much money. PEM fuel cell buses, in my opinion, should be much more exploited. Solid oxide fuel cells are rapidly ramping up. And what's really shown here is fuel cells for stationary and uninterruptible power supply. And my friends at 3M tell me that they alone are supplying enough MEAs to make 15,000 fuel cells a year. So you multiply that by the other major players, we're talking about 50,000 PEM fuel cell systems a year at this point. This market is growing faster than the industry can even account for it. And this is before we account for the Japanese efforts in fuel cells, which will push this to the thousands or tens of thousands of vehicles very, very soon. And the US automakers will have to catch up. But also, of course, membranes are important for membrane reactors, for electrolyzers, for obviously purification, and more importantly for lithium-ion batteries. And the membrane of the lithium-ion batteries is a particularly pathetic material, which I think has a lot of scope to be fixed. As is also the membrane of the alkali fuel cell, which is suddenly becoming of more and more importance. Basically, we boldly exploit obvious chemical morphological transformative hypotheses of ion transformation. So, in other words, we don't have all the theoretical manpower we need yet. But there are some very obvious things that you can intuitively say, I know that if I can fix this, I don't need a computer to tell me to fix this yet. I might need a computer to tell me how to do it, but I don't need a computer to tell me I need to do this. I can basically make a transformative step. And so basically we divide our efforts into 4 parts. One is basically to develop new techniques based on very rapid synchrotron small angle X-ray scattering. Another is a very, very old idea that originated between myself and John Turner back in 1995 to look at some of the tungsten oxide materials that have come out of NREL's photochromic program and see if they can actually hold on to enough water in these PEM materials that they'll still conduct protons at high-end dry conditions. And then some work based on Dan Knaus' ideas of new polymer architectures. These look simple on paper but very hard to execute. And they could really affect ion transport by basically controlling the free volume of polymer. And then some hybrid inorganic organic materials, which actually are looking really exciting.